We will start with Module 3 functions. The prerequisite for this function chapter is set theory. You have to just recall how do we represent sets and other details of the set theories to understand functions. In functions, we have already done Cartesian product relations up to here. Okay, and we are moving on to types of functions and its definitions today. Okay, we will start with the definition. Let A and B be any two non-empty sets. The meaning of non-empty is at least there should be one element in the set. So these two are two sets which are non-empty. Then the function, or it is also called as a mapping, is denoted with F, and it is defined from A to B. A is your set, first set, and B is your second set. Is a relation from A to B. What is the function? Function is a mapping from A to B, which is a relation from A to B, such that for each A in A, there is a unique B in B. Here you have to concentrate on the meaning of unique B. There should be only unique pair. A should connect to unique B, such that when I write both the pairs in ordered pair, it becomes ordered pair of A comma B belongs to F. This is an element of function F. Then we write this representation in the form of B can be written as F of A. Here B is called as an image of A and A is called a pre-image of B. So if we represent through a diagram here, this is my set A and this is my set B. We are trying to define a function F between A and B. Now in this, we have A here and B is the element of B. B is called as image of A because it got paid. A is related to B here. So you call this B as image of A and A is called as pre-image of B under F. That is the definition. Image and pre-image. Always remember that this is called as image because this is getting mapped with this. This is the image of A and A is called as a pre-image of B under F. And it is denoted with B is equal to F of A. Then we call the value of function F for the argument A. A function F from A to B is denoted by F from A to B. That is how we read this F colon A to B. How do we read this as F from A to B, function F from A to B. The pictorial representation is of this form. Now we will also understand few more terminologies which comes under function definitions. It has to emphasize that every function is a relation, which is very important. It's like a note for you. Every function is a relation, but every relation need not be a function because function has a definition called this. This is very important. Each A in A is having a unique B in B. So when you have this condition, then such relation can be called as a functions. Not every relation is a function. Because if R is a relation from A to B, then the element A can be related to two different elements under R. This is not a case in respect of functions from A to B. So when you take A here, B here, and A is having an element A and an element B here, then C, you cannot have this relation. According to this, A cannot map to two different images. It should have always unique image. And one way to remember this, whether this is a function or not, this is actually not a function, where I define another relation A and B here, C is here, and look at this. This can be called as a function. This is only a relation, but not function. This is not a function, but it is a relation. But here, this is relation as well as function. So one easy way to remember, look at the symbol. If you find that a greater than symbol in the pictorial representation, call this as a function. If you find symbol here, anyway, elements of the two set, it is not a function. So that an easy way to remember this. Less not allowed in the function. Greater symbol can be allowed. For the function f from here, A is called as a domain and B is a codomain of what? Of f. F. The subset B, which consists of images of all of A, because it has to map with B elements, and elements are getting mapped with elements, either few elements of the elements of B. That depends on the B. So, the codomain of F range of F, which is denoted F of A. Say, for example, there are elements here which got mapped to this. In that case, this is a subset of B. Only for the subset, all the elements are mapped as a range of A. The following observations are consequences of the definition of a from A to B and other associated definitions. You can also understand definitions along with this. One is every A in A, some pair A comma B belongs to F, and if B1 order B1 belongs to F, like this in terms of diagram. A is there. If I put B1 and B2 in B, and yes, right? A is an element of B, then element of function, right? So as per the definition, there are, it's not unique more than one images, the same element. This cannot happen in the allowed. So this is not possible. Equal to V2. These two has to be equal. There is a relation. Definition: an element B in B need under F. So this is another, and B is here. An element subset. There is B which is outside this subset, and still it is in the B. It's not image. This is not getting mapped onto any values of A. This, extra elements here in set B which are not mapped. So that is another condition. And the third condition is, if an element B in B has a pre-image A in A under F, the pre-image need not be unique. In other words, two different elements of A can have the same image in B. So as my previous explanation, this can happen. Even three elements A, B, C can map to Z. Okay, so that means here you can just observe a greater than symbol is allowed in function. This can happen in the functions. The statements A, comma B belongs to F, A, F, B, and B is equal to F of A are equivalent in the sense that they are carry the same meaning. Both are one and the same meaning. So you have to make sure that A is, how do you write in relations? A is related to B. In functions, A having function with mapping with B, that's all. It is also represented in the form of B is equal to F of A. If G is a function from A to B and denoted by this way, then F is equal to G only with the condition F of A is equal to F of G. Every element of A is an element of B. Then you can say that G is a mapping from A to B. And definition for a range. Definition for a range is F of A is equal to F of X, where F of X set of all X such that X belongs to A. Such that X belongs to A. All the elements X is taken from A. Look at the diagram. A is here and F of A is this. This is called the range. Next is for a function F from A to B, if A1 is a subset of A and F of A1 is defined by in this way. So look at the case. A1 is getting mapped onto only this range. You can call this as image of A1 under F, image of the subset, which is getting mapped onto a subset of the second set or codomain. This is called as a domain and this is called as a codomain. For F from A to B, if B belongs to B and B inverse of B is defined by F inverse of B is equal to set of all X belongs to A such that F of X is B. So that is called as F inverse of B is called as a pre-image set of B under F. So here these are all the images of this and these are all the pre-images of this. So that for that definition is this. You call this as a F inverse of B. All the elements here which are mapped to B, they are the F inverse. So this will help you to compute F inverse in the problems. Next is, again here this is, here only one element is there which is getting mapped, but here a subset is there. That is the difference between these two. You take all the elements of here and find out its pre-image in this subset. So that completes the definition.